A Ufer ground, also known as a concrete-encased electrode, is an acceptable method for earthing a generator pad. It is important to ensure that the Ufer ground consists of at least 20 feet of vertical steel reinforcement embedded within the concrete footing. This reinforcement needs to be effectively connected to the generator's grounding system utilizing a copper bonding wire. A half-inch diameter, 8-foot-long ground rod is sufficient for bonding the generator case to earth, provided that the ground rod is driven at least 8 feet into the ground and the soil where the ground rod is installed has a resistivity of less than 25 ohms per meter. Also, the ground rod must be connected to the generator grounding system using a copper bond wire. When a generator is interconnected with the utility power system, an isolation transformer is recommended. This is to prevent potential ground fault currents from flowing through the generator, ensuring safer operation and minimizing risks of damage to equipment. If the soil resistivity is high, meaning it exceeds 25 ohms per meter, supplemental grounding electrodes may be required. These could include additional ground rods or the installation of buried plates to enhance the grounding effectiveness. All metal objects within the generator area, such as fuel tanks and enclosures, must be electrically bonded to the grounding system. This ensures that all metallic parts are at the same electrical potential, reducing the risk of electrical shock and providing a safe environment. Use a copper ground wire of appropriate size to connect all grounding electrodes and components. Typically, a number 6 American wire gauge or larger is recommended. Selecting the appropriate wire size is critical to handle potential fault currents and ensure a low impedance path to ground. Regularly inspect and test the grounding system to verify its integrity and proper functionality. Routine checks can identify any potential issues, such as corrosion or loose connections, allowing for timely repairs and maintaining a reliable grounding system. The purpose of grounding is to provide a low impedance path for fault currents to return to the source, which helps to quickly trip over current protection devices like circuit breakers or fuses. This rapid response minimizes the duration of fault conditions, reducing the risk of electrical shock, fire hazards, and equipment damage. A properly installed grounding system also helps to stabilize the electrical potential of equipment and enclosures relative to the earth, which minimizes electrical noise and interference. This is particularly important for sensitive electronic equipment that can be affected by voltage fluctuations or stray currents. Grounding ensures that in the event of a fault, the exposed metal parts of equipment do not become energized, protecting individuals from electric shock. Grounding systems typically involve connecting metallic parts of electrical equipment and enclosures to a grounding electrode, which is a conductive object buried in the earth. The grounding electrode provides a low resistance path for fault currents to flow back to the source, tripping the overcurrent protection device and energizing the circuit. There are several types of grounding electrodes commonly used, including ground rods, ground plates, and concrete-encased electrodes, also known as Ufer grounds. Ground rods are metal rods, typically made of copper or copper-clad steel, that are driven vertically into the ground. Ground plates are metal plates buried horizontally in the ground. Ufer grounds consist of a metal rod or conductor encased in concrete. The selection of the appropriate grounding electrode depends on factors such as soil conditions, available space, and local electrical codes. The size and type of grounding conductor used to connect equipment to the grounding electrode are also important considerations. Grounding conductors must be sized appropriately to safely carry the maximum fault current that could occur in the system. The National Electrical Code, NEC, provides detailed requirements for grounding and bonding electrical systems to ensure safety and proper operation. Section 250.4 provides the general requirements for grounding. Section 250.50 covers grounding electrode systems. Section 250.52 specifies the requirements for grounding electrodes. Section 250.66 details the sizing of grounding electrode conductors. Bonding involves connecting all metallic parts of an electrical system together to create a low impedance path for fault currents. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Bonding is typically achieved by connecting metal enclosures, raceways, and equipment grounding conductors to a common grounding point. The equipment grounding conductor (EG) is a critical component of the grounding system. The equipment grounding conductor provides a low impedance path for fault currents to return to the source, tripping the overcurrent protection device. The equipment grounding conductor is typically a copper or aluminum wire that runs alongside the circuit conductors. The size of the equipment grounding conductor is determined by the size of the circuit conductors in accordance with the National Electrical Code, NEC Table 250.122. In addition to grounding and bonding, surge protection is another important aspect of electrical safety. Surge protective devices, SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, power line disturbances, or switching events. Surge protective devices divert excess voltage to ground, preventing it from damaging sensitive electronic equipment. Surge protective devices are typically installed at the service entrance and at sensitive equipment locations. There are several types of surge protective devices available, including metal oxide varistors, MOVs, and silicon avalanche diodes, SADs. Metal oxide varistors are the most common type of surge protective device. They are made of a semiconductor material that exhibits a higher resistance at normal voltages and a lower resistance at high voltages. Silicon avalanche diodes are another type of surge protective device that can provide fast response times and high surge current capabilities. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Inspection should include checking the condition of grounding electrodes, grounding conductors, and bonding connections. Any signs of corrosion, damage, or loose connections should be addressed promptly. Testing the grounding system can verify its integrity and proper operation. Ground resistance testing involves measuring the resistance between the grounding electrode and the earth. A low resistance indicates a good connection to ground. Continuity testing can verify the integrity of grounding conductors and bonding connections. A continuous path indicates a reliable connection. Grounding and bonding are critical for electrical safety and equipment protection. A properly designed and installed grounding system can minimize the risk of electric shock, fire hazards, and equipment damage. Regular inspection and maintenance are essential to ensure the continued effectiveness of the grounding system. Local electrical codes and standards provide detailed requirements for grounding and bonding. Adherence to these requirements is essential for ensuring electrical safety. The selection of grounding electrodes, grounding conductors, and bonding methods should be based on a thorough understanding of the electrical system and the specific site conditions. Consulting with a qualified electrical engineer or electrician is recommended to ensure proper grounding and bonding practices. The National Electrical Code, NEC, Article 250 provides comprehensive requirements for grounding and bonding. Understanding and complying with these requirements is crucial for electrical safety. Grounding electrode systems should be designed to provide a low impedance path to ground. The impedance of the grounding system should be as low as possible to facilitate the flow of fault currents. Grounding conductors should be sized appropriately to handle the maximum fault current that could occur in the system. The size of the grounding conductor is determined by the size of the circuit conductors, as specified in the National Electrical Code, NEC. Bonding connections should be made with approved connectors and methods. Bonding connections should be tight and secure to ensure a reliable electrical connection. Surge protection devices should be selected based on the voltage and current requirements of the equipment being protected. Surge protection devices should be installed in accordance with the manufacturer's instructions. Regular inspection and testing of the grounding system can identify potential problems before they become serious. Inspection should be performed at least annually or more frequently in harsh environments. Ground resistance testing should be performed periodically to verify the integrity of the grounding system. Continuity testing should be performed to verify the integrity of bonding connections. The use of appropriate grounding and bonding techniques can significantly reduce the risk of electrical hazards. Proper grounding and bonding are essential for protecting people and equipment from electrical shock and fire. Grounding and bonding are also important for ensuring the proper operation of electrical equipment. A well-grounded electrical system can minimize electrical noise and interference, improving the performance of sensitive electronic equipment. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Staying up to date in the latest codes and standards is essential for electrical professionals. Continuing education and training are important for maintaining competency in grounding and bonding techniques. Proper grounding and bonding practices require a thorough understanding of electrical principles and safety procedures. Always consult with a qualified electrical professional for assistance with grounding and bonding. Grounding is a crucial aspect of electrical safety that ensures a low impedance path for fault currents, protecting people and equipment from electrical shock and fire hazards. The effectiveness of a grounding system depends on factors such as soil conditions, electrode type, and conductor size. Bonding is another essential component of electrical safety, which involves connecting all metallic parts of an electrical system to create a common electrical potential, minimizing the risk of electric shock. Proper grounding and bonding techniques are crucial for the safe and reliable operation of electrical systems.